people can get settled, it'll help me start sooner.
About 2 minutes.
Okay.
Okay, the next section will start in 2 minutes. Please come back. You can start if you want.
Okay. Okay, welcome back. So we discussed the first two applications. While people are settling in, I'll just summarize those two applications. Uh, the first was decision making. So we looked at how you can make decisions in the future. Then we looked at root cause attribution, how you can explain events in the past. It could be a machine learning model, could be a real world system. Now we look at the third key application, which is out of distribution generalization. So suppose you still want to build better predictive models, but you're finding that your models are not generalizing well. You build them for one hospital, they don't get good accuracy when you deploy them on another hospital, right? Or you build them for one kind of image, maybe it's rotated in a certain way. When at test time you get images rotated in a different way, your model might fail again, right? So there are ways of solving this without using causality, and that's what a lot of this literature is about. So it's either called domain generalization or called group generalization. So in domain generalization, you'll say, I know this problem exists, so what I'll do is I'll collect data from many domains and then learn the common factors that predict my class. If I can do that, then most likely those common factors or invariant factors that affect the outcome should also be the causal factors, right? So that's been one line of work, lots of papers being written, hundreds of papers, on how do you generalize from multiple domains to get a common function, right? And the hope is that is causal. The other is you only have single domain, but you have attributes, right? So remember our face example, we had attributes like pale skin, hair color, and so on for each image. So you have a single data set, but you have lots of attributes. Same principle applies. You can think about equalizing accuracy across all those groups, or you can think about somehow conditioning your model for all those different groups of data so that you build a model that works for all such groups. The hard part, though, is that recently papers are coming out now which show that both of these techniques are not working, right? So what these papers show is that if you take all these data sets, which are common computer vision data sets on this plot, you can think of them as having two kinds of shifts or two kinds of out of distribution. One of them is like rotated MNIST, where just the digits are rotated, right? But it's kind of independent. It's a diversity shift. More directions, more rotations can come in the future. The other is like the colored MNIST data set, which is called a correlation shift. And what that means is that the correlation of a feature may change at test time. So here, for example, color is that correlation. So maybe during training, color means one class, and during testing, the same color might mean a different class, right? But of course, you should not look at color. You should just look at the digit, right? So the expectation is that models should work better on both these axes, but they don't, right? So what they found was that some methods work better on diversity shift, some on correlation, but no method does well on both, right? And what's more damning is that it's not just that they don't work well, they sometimes work worse than doing ERM, which means just fitting the data using the simplest loss error possible. So here, for example, you find that for one of the diversity shifts, MMD works really well, and it works better than ERM. But then if you look at the same algorithm for correlation shift, it was worse than ERM, right? And that's not a good thing, right? What it's really saying is that if you have a new data set for which you do not know which kind of shift it may have, you're just better off doing ERM. And so no method can work well across all kinds of shifts. Another paper came out then. So that earlier one was Ye et al. This one is from Wiles et al. They found exactly the same thing. 2 independent studies just finding the exact same thing. They just define it slightly differently. So they say you might have IID test data, you might have spurious correlation, which is correlation shift, or you might have unseen data shift, which is diversity shift. And they find the same thing. All the methods that they looked at were not consistent across data sets and shifts. So what's going on? Right? And this is, by the way, only on these test or kind of benchmark data sets, which usually only have one of these shifts at test time, right? So a data set might just have a correlation shift, or another data set might have a diversity shift, right? That's just because it's a benchmark. But in the real world, you're going to have multiple shifts together. There's no guarantee. Here's a good example. You have images from satellite images from different locations and different times, right? So now what is happening is at test time, it's not just that the location will change, right? Which correlates with like whether it's a shopping mall or not, right? Perhaps there are more shopping malls in America. So it's not just about the location, the year also might change, the time also might change, and maybe the instrument that you were using to catch these images may also have changed, right? So what we really want to do is not just make models that are good for rotation or color, the 2 examples of diversity shift or correlation shift. In the future, we might want to build models which are good for both kinds of variations at once, right? What if I create a test set which has both color and rotation changed? So now at test time, not only is my input rotated in different ways, it could also be colored in different ways that break the correlation during training. And one thing you might have already noticed is that there seriously is a problem in machine learning if you're not able to solve a task on MNIST. Right? Most people don't even consider MNIST as a data set anymore because it seems like a solved data set. But this problem of out-of-distribution generalization is hard even on MNIST. So here are the results. So what we did is we tried out these algorithms ourselves just to check how would they do if both diversity shift and correlation shift occur in the same test set. So of course, you see that IRM, which is another popular method in the literature, MMD and CMMD. MMD, by the way, is maximum mean discrepancy. It's just a way of ensuring that the 2 kinds of distributions you want to match are close together. So we find that in general, rotation seems to be an easier task. So algorithms get slightly better accuracy than ERM. But when you look at color plus rotation, the accuracy of all algorithms falls. Right? So ERM you expect to fall because it's not considering any of these variations. But then other algorithms also fall. For example, IRM falls from 60 or 50 on individual shifts to about 40 on both shifts. Same for other algorithms. And so what I want to convey today is 2 things. So one, how causal reasoning can help us explain the state of the literature in out-of-distribution generalization. And not just explain, I think the second part I'll show is that it can also tell us how to develop better algorithms which may not suffer from this problem. So the first answer is we can explain them by just thinking about what might be the causal graph that generates our test data. And to the extent that we can generate reasonable graphs, those graphs just themselves will tell you what the problem is in current methods. And I'll talk about those. Essentially, the conditional independences that the graph would dictate whether your algorithm also satisfies them or not. If your learning algorithm does not obey those independences, it's going to fail on that data set. But what's interesting is we'll also show you that no single independence constraint can work for all shifts. So you have to do something different for different data sets based on what graph or what kinds of variations you expect. And then, as I said, we'll also try to show you an algorithm. But I think this algorithm is not the main piece. You can just forget what we built. I think the more interesting part is to understand that you can also look at out-of-distribution generalization through the lens of causality. So of course, these are images, right? We can't build graphs over pixels. We would like to, but I don't know how. So what people do in images is they build kind of causal sketches. They're not really graphs because they're not determining the full data. But they really are just sketches in the sense that you would just have one variable for the entire image, which is x, right? And then you might have one variable for some attributes, and so on. So really you're just capturing the high-level intuitions that you have about the image. And so what we find is that this graph can be a common way of representing a lot of the data sets that people use in practice, right? So let me go through this graph a little bit. So first is that we have x and y. X is the image, y is the prediction, whatever class you're trying to predict. We also assume there is some object, like if it's MNIST, the object perhaps is the written letter, like 1, 2, whoever is writing it. And we believe there's some xc, which are the causal features. This is what everyone wants to learn, but xc is not shaded because xc is not observed. Right? What's happening else? So observed variables, as I mentioned, are x and y. Causal features are xc. We want to learn xc, but they're not observed. Right? What also happens in these data sets is that you have these different kinds of attributes. Some of them might be independent, which I'm calling a int. This is like the rotation. Right? You might find different rotations at test time, but they are just at random. Right? They have nothing to do with the outcome. So here all that it shows is that based on the environment E, you might have some a int like rotation, and that affects what kind of x you get. Right? But then there are other harder kinds of attributes, which are these correlation shift, a not int attributes. So they not only cause your image, like rotation, color, but they might also be correlated with y. So that means they might be associated with what y is in your train set and also your test set, but differently. Right? And then finally, we can also have different a not int relationships. And this is how causality really helps. So you might imagine breaking down this correlation into what's really happening in your data set. So maybe it's just a direct relationship. Y is causing this a not int variable, a cause. Right? Another could be that there's a confounder. Right? So it wasn't like the data set was planned like this. It was just that there is an attribute A, there's an outcome Y. Some other confounder in the world is leading to this correlation. Example would be like the selection bias, sorry, not the selection bias, but confounding bias we discussed, where because of one variable in your data set, it's causing both the outcome and the attribute. And finally comes the selection bias, where you might also just have a data set which was selected in a particular way, like only some kinds of attributes were selected in your data set. Right? Why am I telling you all this? Just to show that this kind of framework allows you to model a large set of data sets that you might encounter in the real world. And if only you can find out what kind of shift you have in your data set, you can then also build a better algorithm to model that shift. So in the MNIST example, rotation would be a int. Doesn't matter, doesn't correlate with the outcome. Color would be a cause, because the way this data set has been created, color and outcome share a correlation. And finally, we'll create a new data set just to test our method, which would be combining both of them. So having a data set which has both attributes, a cause as well as a int. And so our proposed method, CACM, I'll just in a second describe what it does seem to solve this problem, at least for MNIST, where you find that, first of all, both for color and rotation, we can get higher accuracies. 75% is the best here because there's 25% noise. And then for color and rotation, we also suffer. It is a hard problem, but I think it's still better than what other methods are able to give. So the CACM approach can just be summarized in 2 lines. First is we want to identify what kind of domain shift you have. And second, based on that, we want to then automatically give you the correct regularizer. So we'll first derive the correct independence constraints for xc. Because really, we want to model XC, right? So if there's any representation that we are building, it should also satisfy the same constraints that XC, the true causal representation, should satisfy. Right? And then once we have those constraints, we can apply the same constraints as regularizers, as I was mentioning earlier. So step one is to derive those independence constraints. And so the principle is, if g of x is a predictor, it must be having some representation layer, let's call it phi of x. We can just say that phi of x should follow the same conditional independence constraints as xc. So for example, if you had these two graphs, let's say I know that my data set, and this is a limitation, by the way, you need to know what, for now, we'll come back to this, but for now, let's assume that you know that your test set would have this causal kind of variation. Then just looking at this graph and practicing d-separation again, you can find that xc should be independent of a cos given y and e. Right? So this is just based on the d-separation idea that we were discussing earlier. It will also tell us that xc should not be independent of a cos given a. So if there's any method that is enforcing that constraint for this data set, it will fail. Similarly, for confounded, you'll find the opposite. Actually, that constraint was the right one. So you should have used this constraint, which is only conditional on E. And this basically brings up the difficulty of out-of-distribution generalization, that typically people propose methods which have any one constraint, and that's the method, right? But that method would not work for different data sets because there are different constraints that come up. And the second step of our method is then using whatever correct constraint you have identified and putting that into, again, a distribution matching method. And we use MMD because it's a well-trusted method for doing that, right? But the key part is that we change the assumptions. There are adaptive constraints based on the data set properties. Yeah, so I think with that, I'd like to end this session on out-of-distribution generalization as well as the 3 tasks. So one thing I did not mention here, but maybe I'll just say in conclusion, is that this thing must look like a hard thing to assume, because how would you know that the test set has a causal attribute or a confounded one? There are 2 answers to this. The first, if you do not know, then anyways you're going to be in trouble. We have shown results, or you can even prove it very easily using this counter example, that unless you know which regime you're in, your classifier may or may not work, right? It just depends on whether you got the right matching or not. So you have to have adaptive constraints. Now this question of how would you do that in practice, how would you find that out? I think that, again, is just like the causal graph, is an evolving question, a challenge for causal ML. Like if you want to use these tools and give guarantees, then how do you enable people to better identify the kind of test set they have, or have tools for figuring out what kind of data set they may have in the future? Some things you can do, like the satellite data set, I can easily make assumptions as a layman, like, oh, this is a satellite data set, the location is what location is, it's probably not correlated, right? Or maybe the time is more correlated. But in general, I think that's still an open question of how do you formalize methods of representing data sets. So a quick summary for session 1. Causal ML is important whenever you have actions and thinking about effects of actions. We talked about decision making, root cause analysis, and out-of-distribution generalization. The causal graph is the most important assumption. I think it was perhaps Yudia Pearl who said that no cause is in, no cause is out, which means that this is not like Bayesian prior. A causal graph is not a Bayesian prior that you keep increasing the size of the data set, and as n tends to infinity, the prior doesn't matter. It's not that. It would matter even with infinite data. And so this is, I think, both the benefit as well as the limitation. And our goal constantly is to find methods which work with least assumptions, lesser and lesser assumptions. So I gave you an example of debiased ML, which sort of makes no assumptions on the form of the relationships. And also we talked about a high-level graph for images. So you don't have to model the full image, just model the important parts that confound your estimate. Any questions on this part? Yeah.
Yes, on the part that you mentioned about the causal graph on the shift in distribution and covariance, there seems to be two aspects of those. First is the shift exist, and another is how much is the shift have been done. So, but it seems like the causal graph on the overview level, we deal with whether the shift exists or not. So I wonder that do we need to quantify the shift or the cause or effect in our causal graph itself, or we doesn't have to do that?
That's a good question. So we did some experiments. I can point you to our paper where what we show is that if you have the correct constraint in the type of shift, right? It does not matter how strong the variation is, because what you can do is you can even change your regularizer from 0, which would mean that you assume the effect is very low, to a really high value. With large data, it would not matter. I think irrespective of what regularizer lambda, essentially the power you use, you will get almost the same accuracy. So in some sense, with the right type of constraint or the right type of shift, the magnitude does not matter, assuming you have large data. Yeah, I mean, with small data, yes, but assuming you have large data, it's not even sensitive to the regularization constant because it's the right constraint. So empirically, I feel finding the type of constraint is more important.
Got it. So your take is that if we can encode whether the shift exists, or we can at least start with that to get a good performance, right?
Exactly, yeah.
Got it.
From your example, do you have to spell out the shift? What is that B? Or you just put the unknown shift into the model or regularization, or you have to define it? For example, the color is shift or the angle is shift. On the other hand, if you have to define, can we build a model that would predict is that shift or not shift, and put that again in the main model? Is that possible? Have you tried that?
I didn't understand your question. Are you saying, do you know the type of shift?
For example, your E
Yes.
is like a generating distribution of the shift. Do you have to define that, spell out, and put in the model
I see.
what shift is?
So E is optional. Sometimes you may have environments like different data sets or domains. In that case, you might know E. But even if you don't need, if you have a single data set with multiple attributes, E is not needed. So I think all you need to know are the attribute values and the kind of relationship they have.
Thank you.
I was just trying to differentiate between domain generalization, which assumes E is available, versus in-group generalization, which does not assume E is available. So it's optional. Cool. So I think we are a little delayed, but I'm also glad you are keeping up the promise of not letting me finish all my slides. So thank you for that. So we have about 1 hour, or less than 1 hour, right? 45 minutes around? 45 minutes, okay. So we'll try to do the next session in 45 minutes. It's nice because we have some examples which are real-world examples, but I've already given you the framework or the concepts to go through them, right? So I'll try to go through them a little fast, but at the same time, if you have questions, just stop me. The reason I'll do that is because I do want to go to the large language models bit, which I think is quite exciting. And I just want to share that with you so you have that dimension as well. So here are our goals for this session. So we'll first look at the key challenges of applying causal ML. I think some of you have already discussed this through the questions. Then I'll talk about the open source tools. I think this is something that has really changed. So maybe 5-6 years ago, when I was working or starting in Causality, I had to read books which were very complicated, and then somehow write the code as well. And I was very worried that maybe I'm not understanding something well, and so my thing won't work because I just wrote bad code. Right? So at least I think that has changed today. You do have really good open source tools available, which kind of automate a lot of the hard parts of causality. You still need to do the thinking and the formulation of the problem, but I'll describe how these tools make life much easier. And then we'll talk about using these tools for 3 applications: customer rewards program, debugging high latency, so root cause, and finally the MNIST example, how do you classify image under correlation. Once we are done with that, I want to have a discussion or present some results on large language models, especially because this is the only thing I've seen that has the potential to make progress on this causal graph question. Right? So I think all of you have been asking me, where does the graph come from? Where do I know whether this is correlated or causal and so on? And honestly, before 1 year, if you had asked me this question, I had no idea. Right? I was a little dejected because I felt like causal graphs are really hard to get. And without having the causal graph, people are not willing to start doing causal ML. Right? So it was like a chicken and egg problem. But I'm now hopeful that there are ways in which large language models essentially capture the knowledge, the scientific knowledge, the day-to-day knowledge of what causes what. I think people say it on the internet. And I don't think large language models can do causality. They're just learning these kinds of written relationships, right, on the internet. And so somehow they can act as a very good tool to help a domain expert build a graph quickly. So we'll look, as with all sort of hard problems, we'll take that hard problem the last, but then let's look at the easier problems quickly and see what you can do with open source. So I'll talk about the 4 key steps. What's the PyY software ecosystem? And then what libraries are available today in that ecosystem, which are all open source, popular, and easy to use. So I think there are 2 fundamental challenges. The first is the graph. How do you get the graph? And multiple causal assumptions can fit the same data distribution, right? The second is, I think, what one of you asked in the first session. Suppose I even do all this and get an estimate. How do I validate? How do I validate that this is a good estimate, right? How would the mayor know that really giving cycles would improve the health unless they try it, right? Or how would you know when you do this root cause analysis about some system that was really the reason? What if you went back in time and did it, right? That you cannot do. So how do you validate? I think what helps here is that if you do your analysis in a transparent way, and if you clearly communicate what assumptions you're making to reach the answer, and at the end, you try to refute those assumptions to the best of your ability, that's the best way you can follow. Right? If you pay attention, this is exactly the scientific way, which is that you make some hypothesis, you model your assumption as a causal graph. Based on that hypothesis, you identify the effect, let's say use backdoor, then you estimate the outcome, let's say you'd use debiased ML. And then once you have got an answer or a scientific sort of hypothesis, a scientific answer, you're still then trying to refute it using whatever methods you have, right? And so you start with a scientific hypothesis, you get with a scientific theory, and then to the extent that you cannot refute it, like you try all kinds of validation, and it's very hard to disprove it, then perhaps what you have is a very good estimate. Right? That's the idea. So I don't have like a proof for solving these 2 problems. What I do have is a set of steps that you can follow to minimize the chances that you will fall into that problem. And so this was something that I was pained by, as I mentioned earlier. And so I, with some collaborators, developed DoWhy, which is an open source library for doing exactly this thing. And it only focuses on these 2 things. One is having transparent declaration of assumptions, so that not only you know what assumptions are, you can even share it with others and make the analysis better. And second, we have a lot of methods, state-of-the-art methods, on evaluating those assumptions. It's really hard to do it yourself. You can, but I think it's much nicer if you just have a test suite, and given an estimate, you can just run through all of them as you want. So the response has been really good. I think we have now more than 2 million downloads. So I think it's reasonably safe to use it now. Maybe not 4 years back, but I think it's a now stable piece of code. And our goal, of course, is to help people to do end-to-end analysis for causal inference. So I'll just describe to you how we do modeling, identification, and estimation in the DoWhy API. but focus on refutation, because that's one piece we haven't touched so far, right? How do you validate what you got? So let's just break down the causal inference problem one more time, right? Now in a more code-like format. What really happens is you have some input data, some action, some outcome, other variables. Then you have some domain knowledge in your head, maybe. And then the first step is you model the causal mechanism. And so here you want to construct a graph. And what the PyY ecosystem supports is that there's a library called Causal Learn, developed by Professor Kun Zhang and his collaborators at CMU. They are experts in learning the maximum amount of knowledge that you can learn about a graph from data. So you can use that to jumpstart your analysis and create a graph from their algorithm, and then manually edit it further. Second comes the identification step. So remember, this is deseparation, this is backdoor, etc. So DoY helps you there. You don't need to do it yourself. It'll automate it for you. Then the estimation step is done by another library built by some of our colleagues at Microsoft Research, which is EconML. And so this essentially does debiased ML and all the kinds of high-dimensional machine learning estimators. So again, you don't have to worry about that. That's good. Final thing is refutations. You still have to worry about it, but a little bit less because you at least have the tests available with you in DoY, and you can use them to check the robustness of your analysis. And so this sort of evolved differently. It's not like we had this master plan to sort of have these libraries. But I think I'm glad that there's this sort of an open source ecosystem that's just evolving organically. But the result is that now you have libraries available for all these steps, and they also work together. So you just need to use, for example, I'll show you examples. You just need to use DoY, right? And then all these other libraries will just get called for you automatically. And that's the website. I think if you want to contribute, if you're the kind who likes open source, you can also contribute and join us. OK, over to the examples. So first example will be of decision making. Second example, I'll give you of root cause analysis. And the third example, I'll give you for prediction, right? Just following the order that we studied them. So let's say you have a customer loyalty program, and you're trying to see what's the impact of offering this program. Or think of it like discount as well. The same thing works, right? What's the impact of this on my total sales? Now, first, the question is, how do you formulate it as a causal problem, right? Because most people will just give you the English question. Now you can frame it like a counterfactual. You can say, if the current members, who are members of your loyalty program, right, had not signed up for the program, how much less would they have spent? That's your question. It's a counterfactual question, right? You have your current members, they signed up, they made some purchases. You want to know if they had not signed up, how much purchase they would do. And I think in the statistics world, it's called ATT, which is the average treatment effect on the treated, which means you only care about the people who did sign up for your program. You just want to know what would they have done, if not sign up. So you'll have some data set like this. You might have the user ID, sign up month, spend, and treatment, which means whether they signed up or not. And by the way, you can try all of these examples online. I'm just providing you a summary, but they're available, for example, on this link. It's a Jupyter notebook. You can play with it yourself. So step one would be modeling. Of course, we want to create a causal graph. And we are familiar with this graph already. In the first session, I was talking about how you might think about program sign-up, right? But what you do in the code is that you just define a causal model, which tells DoY what data it needs, the graph that you have created, and then what's the treatment, what's the outcome, right? That's the first basic information for setting up the causal model. And the best part is that once you have done that, the rest of the stuff is almost automatic. You don't have to think so much about choices. So for example, for identification, given your graph, you can just say model.identify effect, and DoY is going to run through many identification algorithms and tell you which ones are valid. So for example, here it might tell you backdoor is valid. That's great. It will also tell you what to condition on, and that's pre-spends and sign-up month. But it also tests for instrumental variables. It also tests for front door and many other techniques. With estimation as well, now you have, any method that you want to choose. You can also compare different methods. The call stays the same. It's just model.estimate effect. And then you can choose which method name you want to use. Here I use a method called propensity score matching. It's very similar to the matching idea I presented earlier, but now you're using a propensity model to do that. And so once you do that, you will again get a result. It sort of explains to you what is going on. So first it tells you what the identified expression was. So you do know what you are trying to estimate. Remember the reduction from do operator to a probability distribution. This is exactly just writing that down for you. And then it finally also shows you the estimate, which is 100 in this case. Right? So now we come to the interesting part of causal analysis. Right? 100 is the estimate. So those customers, if they had not signed up, they would have, let's say, spent $100 less or more. I don't remember. But I think that's the estimate. Right? You're getting a 100 number. So now you think about it, right? You obtained this analysis assuming a causal graph. First assumption. Second assumption, you assumed that there were no unobserved confounders. Right? Third assumption, you chose some method, propensity score matching, and you assumed that it was a good method for your data. Any of these can go wrong. Right? And this is not like supervised learning where you have a cross-validation set. Right? I don't have customers who did not sign up and like I was not collecting their data because this is exactly a counterfactual problem, right? Customers either signed up or not. So I don't have any good test set on which to evaluate my models. This is a problem. Right? There are three ways my model estimate can go wrong. The graph is wrong, the identification is wrong, or the estimation is wrong. Right? What do I do? So the best practice I recommend is try as many tests as possible. So these are all necessary tests. They're all like, in scientific theory, you would call them refutation tests. You're just trying to refute the estimate. None of them are confirmatory tests. None of them would say that if you pass this test, then your model is good. All you'll know is that if you fail this test, then there's something wrong. I need to fix it so that that test is not failed. Right? You can also think of them as unit tests, which are testing like, does your causal graph follow the conditional independences in the data? It should, right? Or you can also have integration tests. I'll talk about one or two of them. But the idea is that, is the whole analysis making sense with some known assumption or with some known knowledge? Your whole analysis should match something that you know from outside the analysis. That's the idea. So the first example is the conditional independence refuter. This sort of gets its name from exactly what it's doing. What it's saying is, hey, you gave me this graph based on your domain knowledge or based on some algorithm, right? Let me just test the conditional independences that come from this graph. So for example, this graph says A is independent of B. I can test it in the data, right? So it's a very simple way of just double checking that the graph that you have is reasonable. And if not, you can fix your graph. Another one is called placebo treatment refuter. What it means is, I think you're familiar with AA tests. It's doing exactly the same thing. So suppose you had this original graph, you had some original treatment, you got some effect, 100, right? You got $100, whatever. What you can do is just take the exact same data set and replace the treatment row with something unrelated, let's say a Gaussian random variable. Or sometimes you can do even a better job by selecting something that you know for sure does not have a causal effect on the outcome. But it's still a real variable. And that's a placebo. Right? So what you should expect is that the graph is now like this. Treatment should now not affect the outcome. Right? And if you still find that when you rerun your analysis, you get a non-zero effect, then that shows that there's something wrong in your model. Right? It doesn't tell you what, but at least tell you something wrong. And then you can go ahead and try to fix it. There are other analyses which are more qualitative, so they won't give you a yes or no answer, but they're often the most useful. I think they're called sensitivity analysis, where you're trying to see what if you missed one confounder? How much strong that confounder has to be for you to completely change your decision, right? So what it means is, my estimate was $100. How strong would a confounder be for the estimate to go to 0? And so what you can do is just simulate a confounder like that. It's essentially a Bayesian analysis where you try to simulate some new confounder, introduce it with a specified correlation, and then see how much your estimate changes. So again, this is a little bit difficult because it won't give you a yes or no answer. but it still gives you some nuance to see how robust your estimate is. So we tried this on this data set as well in that same notebook. So when you try the placebo treatment effect, the old effect was 100. The new effect is 0.6, which means after placebo, the effect is almost 0. P-value is not less than 0.05. So this is good. It means the test passed, right? So our model is not dumb. At least it can, if the effect is 0, it can at least give something close to 0. Right? At least that you've changed. The second thing is you can try this sensitivity analysis. So this plot shows you like the power of the unobserved confounder on the treatment on the y-axis, on the outcome on the x-axis. And so basically what you should expect is as you move to the right of this plot, your effect should change. Of course, you're adding a more powerful confounder, so your effect should change, and that's what happens. But it should not change too much, and what you see here is like the scale is about 0.02 on both sides, and the change effect is small. And so that's a good sign again. It's probably saying that you might not be too off if you think it's useful. Any questions here? This is the first case study. I think we'll follow the same format for the next two case studies as well. Yeah.
Hello.
Yeah.
I have a question on in the first step when you model the graph and the confounders that the algorithm like create as a like a block and point to the other attributes. Yeah, like how do they know that the unobserved confounder affect the pre-spends or the sign up month or they just assume from the data or something? Like
So this one is hard because you cannot assume it from the data because the unobserved variable was not in the data. So typically what I've done here is that I've assumed that it affects almost everything here. So I've assumed that it affects pre-spends, affects sign up, whether the decision to sign up, as well as the post-spends, right? So in this case, you just try to make as accepting assumptions as you can based on domain knowledge.
so this graph the connection between the unobserved confounders and the other attributes is you have to define yourself or the algorithm just give it.
No, you have to define it yourself.
Okay, thank you.
For the observed variables, the algorithm will help you. But I think for the unobserved, for the most part, you have to define it yourself.
So like in this case, what does the code model dot identify effect actually compute for this data set? Like maybe some simple explanation.
Sure, yeah. So what it's doing is it takes the treatment, which is program sign up, post spends is the outcome, and it tries to compute different algorithms which will convert the do operator to a probability distribution. So one of the algorithms it will try is called the backdoor criterion, which we discussed earlier. So it will try to find what variables are in the graph such that if I condition on them, the treatment and outcome will be deseparated. So it does a graph algorithm, basically traversing the graph to find this kind of a set of variables. Similarly, it has another algorithm which looks at what variables exist which satisfy the graphical criteria for an instrumental variable, and so on.
Okay, maybe could you like estimate like complexity, like maybe in
Sorry.
it just come up like could you maybe estimate the complexity, like maybe n is the number of nodes in the graph or like connection?
Oh, I think the complexity is bad, so it gets very slow for large graphs. So I would say if you have a graph about 100 nodes, then it's reasonable. Anything above than that, we have to do approximations, like the complexity becomes hard. because you have to traverse all these edges to do that. Yeah.
Thank you. Thank you.
I'm not familiar with this library, but how does the package quantify the uncertainty in each of the estimation? So say if you use the backdoor criterion, you will need to estimate the probability distribution at each of the estimate. And then I think I saw that at the towards the last step, you provide some sort of p-value.
Yeah.
Like how do you even obtain that?
This step you mean? This one, right?
Yeah, because it seems like you need to, like there are so many estimation at each step, and what p-value, like how does it come, where does it come from?
Yeah, that's a good question. So I think because this is like a cascaded estimation steps, it's very hard to use the standard statistical confidence intervals or the p-values. So what we do here is bootstrap or resampling statistics, where in this case, we try to sample a large number of models where this property was changed. And then we try to look at the estimates obtained by the same method over all those runs. So in some sense, we first find out the distribution of estimates of this method that this method would give under assumptions of placebo. And then we see how extreme the current observed estimate is according to that. So all of these are built on certain assumptions. Of course, you have to make some assumptions, like certain assumptions on what can change. And then you have multiple p-values. It's not just one p-value. You'll have multiple p-values based on what assumption you're checking.
Okay, so regarding the library, so I'm just asking in case in the future, like maybe me or anyone trying to use this library, since there are multiple functions and outputs here, yeah, I know that probably like documentation for the library, but in case I like somehow forgot how to interpret these outputs, is there any reference you would recommend?
Yeah, so I will point to a book that I'm writing. I think you can look at that. Also, there's a user guide for the library as well. Both are useful. Yeah, I'll point to the user guide you can search online, but I think the book I'll point to. Yeah. Okay, let's continue in the interest of time. So let's look at case study 2. This is about root cause attribution. The steps remain the same, right? So now you have some data set. This is about a web service. So it has all these kinds of functions like product database, order database. So anytime a user loads a website, all of these services have to load and show relevant pages or parts of the page on a website, right? And then you might see an outlier, right? So your latency of the full website, which can be thought of as the combined latency of all of these functions, comes out to be 2 seconds more than normal. So actually, in the online one, 2 seconds is a large time. You might think 2 seconds is a small, but no, it matters a lot. Even microseconds matter. So now we say, okay, why is this happening, right? Why am I getting so slow? So as I said, the graph here is very simple. The graph is literally the software execution pipeline that you have. So we have this, like the product DB is called to the caching service then goes to product service, blah, 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 and finally your website is loaded. So first, since we are doing root cause, we need one more thing. We need to estimate the SCM as well. And so here we're using a model called structural causal model, which would fit functional forms to each of the nodes. And so we do that, and we can specify the kind of function you want to estimate. Second, then we call this function, which would be an attribute anomalies function. And I think the way this code is constructed looks complicated. But essentially what you're doing is you're trying to attribute the anomalies using the counterfactual algorithm that I described earlier. But then you also want to say, I want to get the confidence intervals. So you wrap the function in that call. And then finally, you can get this kind of a bar plot, which if you remember our face analysis, we used to get like different features and how much each of them is a root cause for the prediction. And so here in the real world, you're getting an attribution score for which service is the main reason that this thing is failing. Right? And so here, perhaps you might say the caching service has now a much bigger change, which was not there earlier. And it has the biggest effect on your final website loading. Similarly, you can use the same library, and I think that's one of the benefits of this ecosystem, is that you can use the same principles, same library for different tasks. So the third task I can show is prediction. So let's take our MNIST example again. I have a data set of rotated MNIST, and I also have a data set at the end, which is a combination of rotation and color. And the task is I want to detect which image it is. So here, of course, graph we've already discussed in length. So does give you this graph by default. If you think, no, you know better about your test set, you can also give a new graph. But for most cases, this default graph would work. All you need to do in the API is just tell us what types of attributes you have and which ones are which, right? So here you say you want to launch a CACM algorithm, CACM, and then you also say that causal and independent are the two attributes I have. And then based on that, automatically DoI would compute which constraints are the correct one. All you need to do is just give that information. And then we can also fit the causal predictor. Underlying, we use PyTorch. But the idea is that once those constraints are given, fitting the predictor is a known problem on how you can do it. And you can get the accuracy and so on to check your method. So with that, I think the practical part, I hope I gave you a nice overview of how you can still use the tools today to make it work. Now, as promised, let's spend the last 15 or so minutes on the future. Right? So one of you asked me, what's the hardest problem? Right? What problem are you working on? So this is one problem I'm working on. And the problem is, how the hell do you get the graph? And if you cannot get the graph, are there other ways? Like, can you circumvent this whole pipeline? Like, are there ways in which you can do causal ML, but maybe you don't need the graph? Right? So this might sound like a bad idea, because then how would you get the guarantees? But at the same time, think about language or think about images. It's unclear whether a graph even exists, right? In the proper form, like from pixels to a graph, or a graph over words, right? But as humans, we still are able to reason over them, right? So I would say those are the two main questions for causal ML in the future. One is better ways of getting the graph, or at least helping the person get the graph. And the second is finding ways which may not require the graph. And maybe there'll be benefits there because they might even scale better. I think, as someone was mentioning, even identification sometimes is hard to scale in graphs. And so now let's come to this problem, right? We kept it for the last. So right now, the results are not good for state-of-the-art methods on causal discovery. Not good in the sense, like, they're not at a level where you can just directly use one of these methods and trust the results. In fact, what happens is, in practice, you can try this. Take any data set and try a couple of different causal discovery algorithms, which give you a graph. They would vary. They would not agree on many edges, and it's unclear which one to trust. Why is that? Right? Let's try to understand why is that. It's not just like the people working on those algorithms have not devoted enough effort. There's a fundamental reason. So let's look at two tasks, pairwise discovery, which is like I give you a pair. I give you, let's say, altitude data and temperature data. And I ask you which one causes which. The second one, we'll look at full graph discovery. And actually, counterintuitively, the full graph discovery is an easier task than pairwise. And I'll talk about that why. So pairwise discovery, the problem is, if you have some observed data, all you get is probability of A and B. Right? You can factorize it in two ways. One, you can say the right factorization is probability of B given A multiplied by probability of A. Or you could say the reverse. Right? The problem is that if you look at the likelihood of any of these factorizations, it's exactly the same. So if you're just trying to fit a maximum likelihood model or any other technique to differentiate which one is the right direction, you would not get any signal. Right? So theoretically, people have shown it's impossible to do this non-parametrically. But recent work, maybe a decade old now, but still working on, is about using some parametric assumptions. So if you assume that maybe there's a non-Gaussian noise in this model, or if maybe the model itself is non-linear, then there are ways in which you can discover the direction with some accuracy. Right? And one of the methods is lingam, if you want to read up about it. So yes, we've made some progress. The results are still not like in the high 90s, but there are now some ways of doing the pairwise problem. Then comes the full discovery problem. Right? So you might think it's a harder problem, but actually it becomes easier because of these three graph structures that I want you to look at. So we've seen this before in D-separation as well, but let me just go through again. So A could be a chain, which means that B causes A causes C, or A could be a fork, which means A causes both of them, or finally A could be a collider, which means both B and C cause A. Right? What's very cool is that the first two have one kind of conditional independence, which is that B is independent of C given A, but the last one has a different way, a different independence, which means B is independent of C, and in fact, if you condition on A, then B and C become dependent. Right? Again, this is all coming from the basics that I had taught earlier. This is just D-separation working. Now that's cool, right? So what that means is if you have a large graph, you just take all triplets of it, and the moment you find this kind of condition, collider condition, where two nodes are independent, but conditional on one more node, they become dependent, then you have identified the direction of the edges, right? So then at least you have identified one triplet in this whole graph. And there's an algorithm called PC, a classic algorithm that uses this knowledge. These algorithms work, but again, it depends to the extent you have colliders in your graph, right? If you have these two kinds of triplets, you'll again be at a loss on what to do. More recent work looks at it from a deep learning lens. They say that we could perhaps just look at it like a continuous optimization problem, where we're not trying to discover specific collider structures. We are just trying to discover any acyclic structure, right? And by using Occam's razor, if there is a nice regularized model that gives you an acyclic structure, maybe that is the true one, right? So that's the state of the art today. And so what we looked at, I think this is very recent work, maybe a few months back, is would LLMs help here? It's a very crazy question to ask, first of all. I admit that. But I think I was at the time sort of looking at what ChatGPT could do, right? Like all of you might have also tried once it came out. And just for fun, I tried causal questions. So I asked it, does smoking cause lung cancer? And it gave me a correct answer, and a reasoned answer, not just like it gets it correct, it also gives me the reason. Like, wow, okay, not impressive. Maybe it says Reddit, right? Then I started asking it more and more harder questions, and it was working, right? It would give me good answers, almost in a spooky way. And if I ask it to explain, it can explain it as well. So I thought, this is cool, right? Because one, let's not get fooled. It's not doing causal discovery, right? All it's doing is it's a very good model that stores all the world's information, and then it can also answer it when you ask in terms of causality, right? So it is doing something interesting. So I thought, let's just try it on the best known benchmark that is available for causal discovery. So I tried with pairwise discovery first. And it's actually a magnificent piece of work by Muij et al. And a lot of people after him who have looked at this, created this data set and also looked at different ways in which you can predict the relationship, right? So it has things from zoology, engineering, biology, atmospheric science. Whatever field you're interested in, you'll find some nodes here, some pairs which are from that field. And then the challenging task is that most existing algorithms used to achieve about 70 to 80% accuracy. The best, I think, was 83%. What I did was something very simple, right? Just like you ask a person, a domain expert, I asked this model. So I would just ask, let's say, does changing A cause a change in B? Please answer yes or no. And I can ask in the reverse as well, does changing B cause A? And I take the mean of those answers. Right? So in the first step, I wanted to make it simple, so I just say, please answer in a single word, yes or no. It's very easy to count. In the second one, I realized that if you ask it to also explain its prediction, it somehow does better. I think this is a kind of chain of thought prompting that people have started using. So in the second template, which I'll call a single template, I ask it both questions at once and just ask it which is more likely. And I also encourage it to let's work it out step by step, in which it just means that it'll also give its explanation. It's also good to debug the answers. So here are two examples to show you how it looks like. So in the first, I'm asking it, abalone is an animal, organism. So changing the age of an abalone causes a change in its length. This is GPT 3.5. It gets it correct and says, yeah, of course. I mean, as things age, it gets increased, right? But then the same model, I asked the same question again, and I just changed the age, the length to diameter, right? So I'm now asking, changing the age of the abalone, does it change the diameter? It gets it wrong. So it is quite unpredictable. And you would think, why is it getting this wrong? Why is it getting this right? I have no idea. If you just try it one more time, it might even get that correct. So it also, there's some random noise. But what's surprising is that at any point with a single random seed, if you run through this whole data set, average accuracies you'll get is around 96% for GPT-4. This is significant because it is about 13 points more than the best known method. And also, it's sort of, you see some nice patterns emerging, right? One is that smaller models can't do it. It's only the bigger models that can even approach this task. And the second is small things like the simple prompt changes make a lot of difference. So just telling it you are a helpful assistant to causal reasoning increases its accuracy by 5%. Right? So again, I mean, there are different methods, right? The point is not to compare them. The first are covariance-based methods, which are more principled. The second, for lack of a better term, let's just call it knowledge-based, right? So this is your knowledge-based LLM, just looking at the world knowledge and telling you what might be the most likely causal direction. But I think the exciting part is combining the two, right, in the future. So for example, here you might have a question about ozone concentration and radiation. The first time you ask the question, LLM will give you the wrong answer. But then when you read its description, you'll realize that it's talking about the stratospheric ozone concentration, whereas the data set was about the city level or the ground level ozone concentration. So these kinds of things I could do because I'm a domain expert here, quote unquote, data set expert. But in the future, you can imagine that you might combine covariate-based knowledge with this kind of knowledge to be able to better kind of correct these errors as well. And so then I got on a path here, right, where I thought maybe this one is easy because it's, again, a popular data set, right? So many papers are written on this data set that maybe it's just memorized the whole data set. So I started looking for more and more obscure data sets. One of them was this so-called neuropathic pain data set, where they just have lots of knowledge about things I don't understand. So I don't know if you would understand either. So things like pharyngeal discomfort or lumbago or thoracal dysfunction, all of these are Greek to me. I have no idea, right? But I have a large language model. I'll put them in the same prompt without knowing anything, and I'll just look at the results that come. Again, I was surprised. The results are good, actually. So in fact, GPT-4 gets 96% again. GPT 3.5 gets 85%. But still, it's kind of much better than what people are able to do using non-LLM methods. And one of the interesting parts is that it also corrects the data set. I had not expected that. So think about it, right? The data sets are also created by researchers, and you have limited time. And it's a large data set. It has 400 edges. You can always miss one or two, right? So in this data set, we got an error, right? So LLM says that obesity should cause L5 radiculopathy. And it also gave me a good reason. And I got convinced. I mean, I don't know this literature anyways. So I thought I should search, right, whether it's true or not. And when I searched, I did find that there are papers which do claim that obesity can cause radiculopathy. And in fact, the answer, if you read, I mean, we don't have time, but if you read the answer, it's a very well logical, reasoned answer that comes up. And so then we thought, let's get ambitious. Let's do the full graph discovery. Right? So now we are interested in getting the full graph, not just pairwise. And there is a 100-pair subsample that's used as a benchmark in this literature, where 50 of them are correct edges, 50 of them are not correct edges. And so now your task is slightly harder. You not only have to say whether the edge exists or not, you also have to say what the direction is. Right? Now, of course, you might be thinking this won't scale, and that's true. I mean, if you have a large graph, that means you have to do n-square prompts. But for now, let's assume the graph is small. You can run through all n-square possible combinations. And let's just add one more question, like A causes B causes A, or nothing causes each other. How would this do? So here we looked at some earlier work by Tu et al., who were also using ChatGPT, but not using the right prompt. I mean, a very simple prompt they used. With some amount of prompt engineering, we were able to increase the F1 from about 0.21 to 0.68, 3 times increase. What does this tell us? One, LLMs are still weird. Like you have to do a lot of prompt engineering. So it's like a dark art. Like you just have to keep playing with them, just forcing them to answer what you want them to answer. I think that thing will improve over the years. Like maybe this will become much more repeatable, much more reproducible, these kinds of results. But also what it's showing is that there is some signal, like LLMs have captured enough information that even for full graph discovery, you can improve your F1 considerably. So finally, I think since some of you are interested in physics, and also I heard someone say climate science. So even I'm interested in that, right? So I thought, can it solve some of the hardest problems known today? And what I mean by solve is just like, it's just helping you get some information that you may not have otherwise. So I looked at this atmospheric science data set. So luckily, there are some researchers who created a causal graph of about 12 variables on exactly this topic. And it has things like the cloud water path, sea level pressure, geopotential height, and other things I don't understand. But essentially, I had a nice benchmark again. It was a causal graph with different variables. And experts had labeled that graph with what the right relationship should be. And those experts also tried some of the recent deep learning algorithms. So they tried no-tiers, they tried DAG-GNN, and they also tried a temporal version of an algorithm. And so they were getting NHD, which is, think of it like SHD. It's just the, like, how many edges are you not getting right? They were getting an NHD of about 0.33. When we tried GPT 3.5, I think we also got something similar. This was nice because I could just do it on the whole data set, right? There are only 12 variables, 48 edges, just do n-square comparisons. But with GPT-4, this reduced to about 0.22, which is again significant, given that this is a real-world data set, and there are active scientists who are trying to kind of study these topics, right? So maybe in the future, if there's a bigger data set that needs to be made, you could use GPT-4 at least to get the first version before releasing it. And of course, you have to edit it, but you can get the first version. But also maybe in the future, like if you want to build models on top of this, a good question to ask is what would happen if you used GPT-4 directly and then maybe had some estimation on top of it? How bad would it be compared to what we have right now, which is nothing? So that's an open question. Like, is it a force towards improving your bias, or is the risk so much that it might just decrease your bias? I think that's an empirical question to look at. But finally, I'll just end in 5 minutes. I know we're over time. So I think for the scientifically minded audience, the first thing that comes up is that, is this even learning? Like, it could just be a memorization, which is true. It is memorization. We had tried it, and we found out that it is memorization. So for example, you can also try a task where you ask GPT-4 to complete this data set. So this data set looks like this, like it has pair 005, it has age, and then the next thing should be length of abalone. If you just ask GPT-4 that you're an assistant which has just read many data sets, and can you please just complete this data set? I've lost part of my data set. Can you just complete it? It can do it with about, I think, 25% overall accuracy in terms of completing that full row. So what this tells us is that it has also learned how to complete data sets. It has most likely memorized this information. But in some sense, this is exactly what we want, right? We exactly want a model that has memorized good relationships from the world and is able to help us augment our graph. So I think while the scientific question of whether LLMs have truly learned something is very important, and that's something people are working on, I'm also working on it, but in practice, it doesn't matter. If all you want to do is build a good causal graph, this will help you, and you can directly use it. So takeaways are LLMs have just brought a new, fresh way of looking at the discovery problem. They are getting some comparative performance, but this is very early work. I just wanted to share it because I think it's good for you to also know what kinds of things people are doing outside of the core causality field. But in the future, I believe maybe this will merge, right? Maybe algorithms like PC can be combined with LLMs. giving you the best of both, robustness as well as coverage of a large domain. Thank you all. I think you've been a very good audience with lots of questions. I'll leave the conclusions up here. You can go through them. If I want to summarize my lecture in 2 parts, one, learn Causal ML because it might be important in certain aspects of decision making, root cause analysis, or prediction. But also, be very careful that your assumptions are what drives your analysis. So the better your assumptions, the better your validation, the better you would have clarity in your analysis. Thank you. I'm here for questions, but I think if people want to leave, have lunch, feel free to. I'll just hang around for a bit in case you want to come up and have any questions.